Saludos a todos. Si creían que el experimento final en la Antártida se trataba solamente de grabar al Sol, están equivocados. Hoy vamos a cubrir otro experimento interesante que realizaron. Este experimento consistió en pesar dos masas referenciales de 500 gramos en la Antártida, usando unas balanzas y pesas que fueron probadas previamente en otros lugares. Concretamente, el experimento fue llevado a cabo por el dueño del canal Critical Think y el objetivo de esto era demostrar la rotación de la Tierra. Se preguntará cómo es eso posible, pues la teoría es bastante simple. Si la Tierra es una esfera en rotación, significa que en el ecuador debe tener una fuerza centrífuga debido a su giro. Una fuerza que, aunque es muy pequeña, tiene un efecto que es medible. Entonces, una masa medida en el ecuador debería tener un peso superior al medirla en los polos, en donde no hay fuerza centrífuga, ya que allí la velocidad de rotación es prácticamente nula. Dejaré que sea el propio Critical Think quien lo explique.
So here's the theory. I'll quickly go over this. I've covered it in previous videos, but I think it helps to just go over it one more time. So there's the force of gravity acting on us as we stand on our wonderful globe, and that generates a downward force of about 9.8 newtons. And the force due to centrifugal effect, which the tendency to throw you off the planet, is only about 0.034 newtons. So for all those people that think it's like a spinning tennis ball and the water should fling off the planet, just look at the difference there. The downward force is much greater than the flinging off the planet force, but it's measurable. And here's the theory. So at the equator, because the Earth is an oblate spheroid, gravity is a little bit less at the equator, and the centrifugal force is the greatest, because that's the highest rate of spin. 1,000 miles per hour, remember. So that generates a force of about 0.034 newtons. Now, this example here calculated at 30 degrees. So the force of gravity is a little bit more because the radius is a little bit less. And there's the centrifugal force operates perpendicular to the axis of rotation. So it will have a vertical component and a horizontal component, Fy and Fx. Calculate that out. And at 30 degrees latitude, it's 0.0255. So as you move away from the equator, something will start to weigh heavier if you don't change the scales, if you keep the scales at the same calibration.
Bien, pasemos a explicar ahora cómo es que se ha planificado el experimento. Critical Think vive en una ciudad de Australia llamada Redcliffe, la cual se encuentra en la latitud 27 sur. Por lo tanto, allí es donde ha establecido lo que será la latitud de calibración. Su balanza será calibrada para establecer que 1 kilogramo es exacto en esa latitud. Luego lo que hará es llevarse su balanza y sus masas referenciales en sus viajes a otros lugares del mundo. De modo que se obtendrán valores de pesos menores o mayores respecto de dicha latitud según a las latitudes que viaje. Pasemos, pues, a ver los videos con las diferentes mediciones.
Well, g'day, floodies and reality defenders. We're going to check the calibration. We're at the original calibration point for the scales. And we've travelled around a bit and see what we got. So that's a slightly different value, slightly higher than when we originally left, but still very, very close. Well, g'day, floodies and reality defenders. It's Critical Think from Down Under. We're taking a reading today from Konkan. And we'll see, let that settle down. That's around about 30. That's not too bad. That's pretty close to the expected value. We wait for it to go back to 0. We'll try this again. And Let it settle down again, and we should get 30, 29, something like that. So that's in Concan. Well, g'day flatties and reality defenders, it's Critical Think from Down Under, and I'm currently in the Latham VIP lounge. I'm going to take my Santiago measurement, and the prediction is 1000.36. So we'll call 1000.33. And we'll just check the scales and repeat. A little bit of floor movement. So 1033.34, pretty much spot on. Portrait, I got something very important to do with the weight measurement at Union Glacier. I've got to repeat it in a more stable environment, and here we are. I'm going to turn this around. Here we are in the dining hall, and I've got this set up on the serving bench, which is probably the most level place in the whole Union Glacier. So I've got 0.1 degrees there, and 0.1. This is the best place to do the measurement. So we're going to go ahead with the best scale I got, which the prediction is 1003.80. So down there outside it was 1003, we weighed it around about 76. So in here a little bit more stable environment, it's a little bit more 1000, but it's still 1003 is settled down to 0.82, which is 0.02 of a gram from what was predicted. Now I have a 500 gram scale here, and this one, if you make half of 3.8, what's that, 17, I think. So there we go, 501.76, which is about the correct weight. Now this scale here, this is my backup scale. It's not quite as accurate as the other one. Its calibration is slightly different, but it still gives correlated results between measurements. So it's slightly lower. It has been slightly lower, but this is due to calibration. Not every scale can calibrate exactly. My first scale has an exact calibration. This one is it will read slightly lower, but all the readings relative to each other are accurate. So there you go. This is fantastic. This is evidence of a oblate rotating spheroid. Very good evidence that cannot be disputed. If you're going to try and dispute it, then you're going to need to propose a different method of calculation and a different method of predicting, and then go out and measure it, as I have done. So well, Merry Christmas, floodies and reality defenders. This is Critical Think from Down Under. We're doing a calibration check after we come back from the final experiment. These scales have been to Antarctica and back, and we wait for this to settle down. 1000.01 or 2 thereabouts. We'll just do this again. Go on to 0. $1,000.02. So that's retained calibration very well. Started out at 1000.01.
Vamos ahora a resumir los datos que estos videos nos han mostrado. Hemos pasado de tener 999,30 gramos en la latitud 16 norte a tener 1003,83 gramos en la latitud 79 sur. Eso nos da una diferencia de peso máxima registrada de 4,5 gramos. De haber hecho una medida justo en el ecuador, la diferencia de peso habría sido aún más grande, pero ya con esto tenemos una variación bastante apreciable. Y claramente vemos como al acercarnos al ecuador las cosas pesan menos y al alejarnos del ecuador el peso de las cosas aumenta, tal como el modelo esférico en rotación predice que debería suceder. Y no solo es que lo prediga de forma general, es que nos da predicciones exactas de cuánto debe variar ese peso. Critical Think nos ha hecho unas gráficas mostrándonos cómo se ajustan las medidas tomadas por él mismo con los valores de peso teórico que debería tener una masa de 1 kilo en dichas latitudes. Vamos a verlas.
So now we go into the analysis, and so the red line here is the WGS 84, assuming the calibration is correct. The green line there is what we measured on the scale, and so you can see there are some differences. So this is the return journey and this is the go-to journey. So it's all, even though it's not as accurate as the other scale, it's still very, very accurate. And this is how accurate this is. The WGS 84 model explains 99.6% of the variation. So even with a little bit of variation like that, it's because all the dots are in the right place, that where the WGS 84 model says they should be, then that's a very high correlation. And people try to tell me that, oh, you haven't taken into account air pressure, magnetism, whatever. Yeah, okay, so how can those random factors line up exactly with how the WGS 84 model predicts? So, I don't know, but maybe you're trying to tell me that 100 monkeys on 100 typewriters can easily type a novel, because that's the same scenario.
Tengamos en cuenta que Critical Think ha realizado comprobaciones de la calibración tanto antes del viaje como después de volver del viaje, para asegurarse que no había ningún cambio en el funcionamiento de la balanza luego de todos los traslados, por lo que las medidas como tal son confiables. Y no tiene ningún sentido apelar a cosas como presión atmosférica o magnetismo cuando los resultados encajan perfectamente con las predicciones que obtienes de calcular. El cambio de peso que tendría un objeto sobre una tierra esférica con gravedad, rotación y fuerza centrífuga. Cualquier otro efecto daría valores que no tendrían sentido con la predicción. Para resumir, este experimento confirma las predicciones realizadas por el modelo de tierra esférica en rotación, que indica que debe haber un cambio de peso específico en los objetos a medida que te alejas del ecuador. Y estas mediciones, desde Tailandia hasta la Antártida, confirman esa predicción. Ni siquiera le preguntaremos a los terraplanistas, como predeciría su modelo, que haya un cambio de peso en los objetos a medida que te acercas a los muros de hielo de su mundo pizza, ya que ellos ni siquiera saben o pueden explicar por qué pesan los objetos, mucho menos pueden hacer ninguna predicción o cálculo sobre ellos. Espero que les haya gustado el video. Nos vemos en el siguiente.